How to make an engine more efficient? This was the quest with which the thermodynamics started. Let's consider water moving from a body at a higher altitude to a lower altitude. That means from higher potential energy to a lower potential energy. The water moves with certain kinetic energy. In its path, if a turbine is introduced, it starts rotating. This mechanical work comes from the kinetic energy of the water. Similarly, we can consider heat flow from a body at a higher temperature to a body at a lower temperature with the fluid. In other words, from high internal energy to low internal energy. In the process, it can do some work which comes from the heat. This device which converts heat to work is an engine. Instead of this kind of diagram, we'll use a different one which better resembles a practical engine. From the top body at a high temperature, heat Q1 is supplied to the engine. Part of it gets converted into work by the engine, and the remaining heat Q2 is rejected down to a body at a lower temperature. But why not convert the entire heat supplied Q1 to W? Why should some heat be rejected? We will learn in this video that it is never possible to make an engine that can do that. Let's see how. Before that, a word of caution. To understand further, it is important that you are familiar with reversible, irreversible, isothermal and adiabatic processes. Last few videos in this series dealt with these ideas. It is assumed that these ideas are there in your mind. Otherwise, it is highly recommended to watch those videos and come back. Let's say a reversible isothermal process occurs in an engine that takes a gas from state 1 to state 2 by expansion. The work done by the gas is the area under the curve. The heat supplied is Q to maintain the temperature constant. It is converted completely into work. Now we may wonder, is it possible to extract work like this continuously? Can we keep on expanding the gas? Not possible, right? The engine has a fixed size, so we have to bring back the piston to its original position. In other words, bring the gas to state 1 so that we can restart the process again. What does it mean? It means we have to operate the engine only in cycles. Start from state 1 and keep coming back to state 1. Now, if we simply reverse the isothermal process to reach state 1, during the backward process, work is done on the gas which is equal to the work done in the forward process but a negative value. Therefore, there is no net work done. If you see what happens to the heat rejected out is also equal to the heat taken in. Ultimately, nothing happens in a cycle like this. Therefore, one thing is clear. In order to obtain any net amount of work, do not reverse a process in the same path. Now, what about a cycle like this? We go forward in a path like this. The work done by the gas is this much. Now, reverse in a different path so that the work done on the gas is lower. Now, there is a net amount of work. The heat taken in and rejected out are also different. What happens in this cycle? The supplied heat Q1 is converted into two parts, the net amount of work and the rejected heat. Or in other words, the work done is the difference between Q1 and Q2. One thing to note is that there is some heat which is rejected out. Otherwise, it is impossible to bring the gas back to state 1 to start the cycle again. So the conclusion is this. As long as we operate in cycles, some heat is always rejected out. In fact, the method to quantify how good is an engine is to see how much of the supplied heat is converted to work. The quantity used for this purpose is the efficiency, eta. It tells us that how much of the supplied heat is converted to work. W divided by Q1 or Q1 minus Q2 divided by Q1 since W is Q1 minus Q2. The question is, if we have to operate an engine only in cycles, what maximum efficiency is achievable? What is the maximum value of eta? This was the question asked by Carnot. Now, which cycle of processes will give the maximum efficiency? What we already know is that reversible processes give maximum work. So, a cycle with only reversible processes is obviously going to give the maximum eta. And again, only thing that we must make sure is that the backward processes are not in the same path. Carnot proposed an engine which has only reversible steps, which will yield a net amount of work. There are other engines with cycles called as Stirling cycle or Ericsson cycle, which also use only reversible steps. They all have the same efficiency. Here we will focus about only Carnot engine. Let's represent the Carnot engine's reversible steps in a PV space. State 1 to state 2 through isothermal expansion. Heat Q1 is supplied in this step to maintain the temperature constant. Then an adiabatic expansion from state 2 to state 3. It's adiabatic, so no heat exchange takes place. Now reversing to state 1 through 2 steps. One is isothermal compression to state 4. Here heat Q2 is rejected to maintain the temperature constant, otherwise the gas will be heated up. Then an adiabatic compression to state 1. Again, it's adiabatic, so no heat exchange is involved. These are the 4 steps. Now, if the area under each of these curves is calculated and added, a net amount of work will be the answer, which is this area. This is the work done by the engine during the cycle. Now, let's go for Carnot's ultimate quest, the efficiency. Let's calculate it. Eta is equal to W divided by Q1 or Q1 minus Q2 divided by Q1, which is equal to 1 minus Q2 by Q1. Let's use our knowledge of isothermal and adiabatic processes to go further. Q2 is the heat rejected in isothermal compression step and Q1 is the heat supplied in isothermal expansion step. Since it is isothermal process, Q1 is equal to work done in the step 1. As we have already seen in the video calculation of work, it is equal to nRT1 natural log of V2 divided by V1. Similarly, Q2 is equal to nRT2 natural log of V4 divided by V3. Substituting these two Q expressions into the efficiency equation, we get this. Now consider the adiabatic steps. We have already derived that Vt power Cv divided by R is a constant. For the adiabatic step of state 2 to state 3, we can write this. Similarly, for state 4 to state 1, we can write this. When we divide these two equations, we get V2 divided by V1 is equal to V3 divided by V4. Let us use this in the efficiency equation. Finally, we get eta equals 1 minus T2 divided by T1. Amazingly simple but profound expression. Nothing but the temperature difference between the hot and cold bodies between which the engine works is going to be the deciding factor for the efficiency of an engine. This is the great discovery of Carnot. There is something very interesting in this derivation, which is also very obvious. It was seen, however, by Clausius for the first time. We'll see about it in the next video. See you.